a loop like this, and then a toy, move with an initial velocity v, and then go to the top and go down, like a circuit, like in a amusement park. Calculate the minimum speed with which a cart must enter the loop so that it does not fall off at the highest point, at the top. Okay, predict the speed at the top of it in this case. The condition so that it does not fall off at the highest point is that the normal force at the highest point is still greater than or at least equal to 0. Okay, the cart is here and it is still in contact with the loop, and therefore there's still some normal force, or at least it is 0. Okay. Normal force is just the reaction force, like when you're sitting on a chair, the normal force of the chair acts on your body. The centripetal force, Fc, centripetal force at the top here is downward, is vertically downward. It is the sum of the weight and the normal force, just similar to the last case, the previous case, the string, okay, tension and the weight add up to be the centripetal force, okay, and in this case the normal force and the weight, and that centripetal force equal to mv square. V here is weight, v at the top, okay, square doesn't mean the maximum speed, but v at the top, okay. V at the top here is minimum actually. V square over r is the radius of the loop. So the normal force greater than 0, the normal force is the centripetal force mv top square divided radius minus the weight, which is mg, and it must be greater than or equal to 0, at least 0. So calculate minimum speed, meaning the speed at the bottom. The question is to find the speed at the bottom, the initial speed. So from this equation, we determine the velocity at the top, okay, will be equal to g. And if it is minimum, so I'm going to write v minimum here, v minimum, so that we use the equal sign here, okay, equal sign instead of the greater sign, okay. Yep. It will be equal to g times r square root, gr square root, okay. This is the minimum velocity at the top, so that it does not fall down. And then to find the velocity at the bottom, the initial velocity, we will use the conservation of energy. And we ignore the loss of energy in friction. Assume that the friction is negligible. The loss in energy due to friction is negligible because it is not mentioned, so we don't know how big the friction force is and how much work it does. So in reality, in this calculation, we ignore the loss of energy due to friction. So our calculation, the value of the initial velocity will be less than the actual value. Because in reality, you need to provide more energy to overcome the friction, okay? To overcome the work done by friction. Therefore, this calculation, because we do not know friction, is just the perfect case when there's no friction. Conservation of energy. At the bottom, initial energy is kinetic energy 1/2 mv square. This is V initial, okay? Yep. And the potential energy to be 0. We consider the ground potential is 0, okay? Yep. Equal to the energy at the top, which is kinetic energy 1/2 mv top is the minimum speed square, and added with the potential energy, which is mg times the height. The height is twice the radius, the diameter of the circle, which is 2 pi. Okay. Yep. And therefore we can find the initial velocity. V here is we can remove m from the equation here, and then multiplying by 2 so that we do not get 1/2. Okay, the velocity will be v mean square, which is gr. Okay, and then plus 2 times 2 and 2 is 4 gr here, which makes 5gr, right? 5gr. Okay.
Yep.
Because v mean square here is gr. In fact, v actual greater than 5gr to overcome friction.